So in this module, I will show you how to solve partial differential equation, and we call PDE in MATLAB. So I will show you two examples. The first one is single equation PDE. The second one is multiple equation PDE. And you should watch these four modules before you watch this module. It will help you a lot to understand this module. So I want to just give you a brief introduction of PDE and what's different between ODE, right? Ordinary differential equation, and PDE. So you can see this is one example of ODE, and you can see this level, liquid level, right? For example, H. So in this model, we assume that H is the same in different locations. So different this location, for example, X. So there is it's homogeneous, right? So different from ODE and the PDE, actually we consider the spatial heterogeneity. So for example, we have the derivatives over the space variables X. So for the ODE, we only have the derivative, right, over time. So dy dt. So we don't have dy, for example, partial differential equation y over x, right? We don't have t. So this is ODE. So PDE have the right, and then the partial derivative over the space variable. So typically we could rewrite this one as ut, and this one as ux as, right, the second order derivatives of u over x. So just keep this in mind, right? The difference between PDE and ODE is in PDE we need to consider the spatial heterogeneity. So to solve ODE and PDE, we need to define the initial condition, and typically is the variable value at time 0. For example, t equals 0 for the h, right? Typically for the beginning time. So we call the initial condition. So for both ODE and PDE, we need to specify the initial condition. For example, this is the example of initial condition for the PDE, right? So for different location x, and then at time equal to 0, and then we get the value of u. Different from MP and ODE, so this for the PDE we need to define the boundary condition. So this is something we need to take care of specifically in PDE. So there's two types of boundary conditions. The first one, and typically we call the directly condition. Sometimes we call it first type condition. So here's one example. So first type condition typically is the value. So this is the variable's value, right? And at the location 0, the second one is the location. So the first one is anytime, means t means anytime. So for anytime t and at the location 0, the u equals 0, right? So this is the variable's name, the variable's value. So this is the value of the variable. So this is the first type of boundary condition. We also call directly. The second one, boundary condition we call Newman boundary condition. We also call second type of boundary condition. So different from the first type of condition, in the second condition we have the derivative. So we get the derivative of u over x at time, anytime, and location. So this again, this is location, right? And then this means anytime. So at anytime, and the derivative of u over x and in the location 1 always equals 0, means u does not change with x at that location, right? So this is called boundary condition. So boundary conditions are needed to solve ODE, to solve PDE. Okay. Now I want to show you the general procedure to solve PDE in MATLAB, and then give you 2 examples. So typically you need to define the PDE function, and then you define boundary condition function, initial condition. So this is the name of the function you define. You could change the name, right? But you need to keep the name consistent. For example, you should put the PDE function here, initial function here, and then the boundary function here, right? And then after that, you just use the PDE. PE is the server to solve it. So at the same time, you also need to specify the geometry. For example, m equal to 1 is 0 means there's no symmetry, right? M equal to 1 means this cylindrical symmetry, and then m is 2 means spherical symmetry. Okay, so this is general procedure. Now I want to give you 2 examples, and then to show you step by step how to build PDE in MATLAB. So for example, this is the heat equation. So this is the PDE, and this one, right? This one is the first type of boundary condition, as directly boundary condition, right? And this is initial condition. Okay. Now let's take a look how we're going to represent the PDE in MATLAB, right? So typically we represent the PDE in MATLAB in this format. Okay. And then this the PDE, and so this PDE, and this is boundary condition, and this is initial condition. Now so what you should do is you compare our PDE equation with the standard format, and then based on that we need to specify what's C value, what's the M value, what's the B value, what's the S value, and then after that we type it in MATLAB, and then we solve the PDE. So for example, you need to put what are these values here, the variables. Okay, now let's take a look. Now let's build a PDE function here. So now let's take a look of these 2 equations, right? I use the blue color. These 2 equations. So you get UT algebraic equation, and then we move the UXS to the right hand side, just be consistent. So you can see, so UT, so therefore C equal to 1, right? So you get C equal to 1. So you can see, so in our PDE we don't have anything right here. So this M equal to 0. So therefore this M equal to 0, this equal to 1. Okay, and then now let's compare these 2 terms, right? This term here, the partial derivative term with UXS, right? Yes, it means what? D UX over DS, right? Second order derivative of US over X, U over X. So therefore, compare this term with this term here. So you can see the B equal to what? The B should be equal to this one, right? The B should be equal to this one. This should be the same, right? So therefore, the B equal to US. Okay. So now let's take a look of here. So after UXS we have 0, right? We don't have anything here. So therefore, this one equal to S should be equal to 0. Okay. So therefore, we get CMBS, and then after that we could type we build function for the partial PDE, right? So now let's work together. So we get the new, right, script, and then you just type the function, and then remember you need to save the function in the same name as the document, right? So we get function, so CBS equal to PDE equation 1. So the input here is x, t, u, du, dx. So be careful, right? You use the same format that's specified by MATLAB, for example, du and dx. Okay, so now, so we know that c equal to 1. right? And then b equal to du dx, and then x equals 0, right? That's it. Save it. Again, as the same, the document should have the same name as the function. So we are done with the ODE model. Now let's work on the boundary condition. So let's take a look. The boundary condition. So the boundary condition, let's take a look of the first one, and ut 0. Actually 0 means, right, we change, so the value here x change from 0 to 1, right? So therefore 0 means left hand side, and then 1 means right hand side. So you can see here is the s left, s right. Okay, so now let's work on the well, s left first. So s left here is the boundary condition is here, right? When x equals 0, right, you get u t 0 equals 0. Okay, so therefore let's compare these two equations here. The right hand side the same as the 0, and then you can see, remember this b equal to what? B, remember b equal to ux, right? So this one is, this term equals ux. But do we have us on the right hand side of the boundary condition? So for this boundary condition here, for this boundary condition, we don't have us. No us on the left hand side. So therefore, because b equal to us, right? We don't want to keep the us, so therefore we need to set this one, the q, and so we need to set this one q as l t equals 0, right? So this equals 0, and then we compare these two equations, right? These two equations, this 1, this 2, right? So for this equation, this whole term equals 0, right? So compare these two equations, we could compare, and then we could get the conclusion that the p should equal to u, right? So we get p as l and tu equal to u, right? So now x equals 0, right? And then we get t0, and then we call this one as u l. L means left, right? 0 here, 0 means left. Okay, so that's why we get this one. That's why, let me see. That's why we get q as l t equals 0, then p as l t u equals u l. Okay, right here. Okay, now let's work on the right hand side. So the right hand side, the boundary condition we write here is u t1 equal to 1, right? So again, you can see on this boundary condition 7, so the right hand side is equal to 0. So therefore we move, so we organize this equation. We move 1 to the left hand side, so we get -1 equals 0. Okay, and then now let's compare the coefficient. Right, again we don't have this term. Actually is u x, right? It's the derivative of u over s. We don't want to keep this term here, right? Because we don't see u x in this term, right? In the left hand side of this equation. Therefore we have to put this q, we have to put q as r t equals 0, right? So after that, we compare these two equations here. These two, this we call 3, and this equal 4, right? And then in the equation 3, this whole term equals 0, right? Okay, so we compare these two, and then we could get conclusions that p as r tu actually equal to what? U t1 minus 1, right? The whole term here. Again, we could recall ut1 as u right, right? Because 1 it means what? Right hand side, okay? ur minus 1. So that's why you get ur minus 1 here, right? For the pxrtu, and then for the qsrt equals 0. Okay, so now let's type in, based on this, we could type in the boundary condition here. So you can see PL, QL, PR, QR, right? And now let's type this boundary condition in. So build a new function. Okay, and then just type in is function C here. So we get function PL, QL, PR, QR equal BC boundary function. Put 1 here because this example 1. You could change the name, but be careful, right? If you use this, change the name, you use the same name when you use the PDE server. Okay, so we get SR UR. Okay, and then we can type in the boundary condition here. We get PL equal to UL, QL equal to 0, PR equal to UR minus 1, QR equal to 0. Save it. Okay. So the last one is, I think, is for the before we run the simulation, and is we need to set up the initial condition. This one actually is easiest one, right? Remember the initial condition is here, right? This is initial condition, right? U0x at time 0, right? This is the output, right? It's 2s over 1s squared. So we get function value equal to initial function 1. Again, you could change the name of the function, right? You get value equal to 2 times x over 1 plus s squared, right? Okay, plus this actually the semicolon. So save it. Okay, now after we define the PDE initial condition, boundary condition, we're going to use the server to solve it, right? So again, before we do the simulation, we need to again m equal to 0, right? Remember, m equal here is equal to 0, right? M equal to 0. Okay, and then we need to discretize the space, right, and the time. So this means means x change from 0 to 1, and with 20 points sample between 0 and 1. So similarly for the time, we have 10 pound samples between 0 and 1. So after that, we put s and t in, then we put all this function in, and we use the PDE PE this server to solve the PDE. So U now, and we have two columns, right? The first one is the time, the second one is the location. Okay, so anyway, you could use this function serve to plot the 3D, right, representation of the output. So this x, this is the time, and this is u. Okay, so we could change the as y z label. Okay, now let's type this equation let's type this. We call this main function, right? So here we get add a main, save it. It's main PDE 1. Okay. So I say m equal to 0, s equal to link space. Right, if we change from 0 to 1, we have 20 points sample, and then we get t. Similarly, you got link space. We get change from 0 to 1. So we normalize the input, the space and time. So you get 0 to 1, and then you get 10 sample time points. So you get u equal to PDE PE. So again, we get m. We already had the equation, right? PDE equation 1. PDE equation 1. So you get initial function 1, and then we have boundary function 1, then you have s and t. So after that, you could get the 3D dimensions of the output, right? And then you get title. Then you get surface plot of solution. So you get S label. S label equal to distance x. Y label. You get time t. And the last one is Z label. This means pause, means waiting for the keyboard, and then if you do anything, and then you go, the figure is closed. Anyway, you don't have to put it in, right? So this Z label. So you get U. Okay, just save it, and then you could run it. So something's wrong because the name of the function is not consistent. It should be initial. Okay, so I missed I here. So run it again. It should be function. Okay, so run again. Okay, this, be careful, this should be UL. So here, error condition should be UL. It should be UL. Okay, let's go back. Save it. This will be PL. Let me see. This will be PL. Okay, now we get a solution here, right? But anyway, sometimes you need to be careful. We only have L and R, maybe they have 1. Okay, now if you want to show, I want to show you. If you want to show, the output over different location. So first of all, right, remember U. The first column is time. The second column is the location. Right, and then you can see, and U. So now we want to pop time equal to 0, right? The first one here, U1, 1 means the first time point. So we want to get the first time point. Okay, and then you get this profile. So and then I want to show you So if we want to get other tampons here, we change the first index here from 1 to 2 and 3 and to last tampon. So after that, so and then we get a movie. So you can see we get the profile, and then we pause 1 minute, 1 second, actually 1 second, pause 1 second between the two adjacent figures, so that we could see a movie. So we at different time points. Okay, now let me show you this one first. So now if you just want to get one figure, right, what's the yield at different location at time 0, and then you could, so now we want to get a new figure, so we could put figure here, then we put so maybe I should still put pause and close. Pause and close means if you do anything. Pause means waiting for the keyboard. If you do anything, and then close, right? Okay, now let me show you how to get clock. SU here is 1, the first time pong, they get title U at t equals 0. Okay, then S label, and then we get distance X, Y label, this be U, and then pause and close. And now let's get this one done first. Okay, this see the computer waiting for any command from the keyboard, right? So I click and then close. And then you see you will get them right the U at different location at time 0. Okay, now let's do the movie, right? The movie you could do the movie, and you use the for loops here. Okay, now so to do the movie, so we could going to get figure and equal to clock. So we want to keep the figure, right? U1 means U1 means the first tampon, right? 1 means the first tampon. Okay, and then we get 4 and, right? So type it in pair, right? K equal to 2 and to the number of the sampling tampons. Then you can set figure. So we're going to change the S label and Y label, S data, right? S data we change to X, we change to Y data, change to, right, UK means the case as sampling point, right, time point. Okay, so we choose this one, and then we again you copy the S label and Y label, S label and Y label, and then you get the pause, right? Pause 1 second, so you get pause 1 second. Okay, save it. Now run it again. You're going to get the figure first, right? The surface figure first. Some so you get the surface. Then this one. Now let's take a look, so you can see the movie. So you change it over time here. Okay, and then stable, right? Okay, so we are done with the first example. Now let's move to the second example. That we had 2 equations here. So this equation 1, equation 2, right? And also this these are the boundary conditions here, right? So if you remember, right? And this 2 we call is directly, right? Condition, directly, the first type of boundary condition, and this 2 and we call it Newman, right? And the second type of boundary condition. And these two are initial condition, right? Okay, now so for the multiple PDE, typically MATLAB represent the PDE in this way. So similarly, we could compare. So we could compare. You should compare the equation. So now let's take a look. Right. So first, let's compare these two equations, right? The first one with the first one. So you can see, compare this U1t, so this you can see that the C1 equal to 1, right? And now similarly, you compare this term here, so you can see this should be 0, I think it should be 1, so m equal to 0, right? And then this one is equal to what? U equal to U1x, right? So you get you get du1s dx, then you get u1sx, right? Second below here. Okay. So b1 equal to u1x. So so you can see, compare this one, you can get, right, this is equal to s1. Okay. So similarly, you could do that. You could do that, and for the second equation. So you get here. So C1 equal to 1, so C is a vector, right? B is also a vector, okay, and X also is a vector, okay. So after that, M equal to 0, right? As I mentioned. Again, I go through this a bit quick, but you could compare the thing, compare this second equation, you could get a similar conclusion. Right. Now let's type the second PDE here. So we got second PDE. So we get function CBS equal to PDE equation 2 STU du dx. Right, so C is a vector, right? Remember, it's 1 and 1. And B, so B is du dx1 du dx2. So we could call B equal to dx1 times, and remember, and this is a vector 2. You had du ds1 du ds2, so therefore you have to put a dot here. Okay, so you get dot times du dx as this vector, right? Okay, and then you get s equal to just u1 times 1 minus u1 minus u2 u1 u2. Okay, so we have the second row is u2 times 1 minus u1 minus u2. So just be careful with the parentheses. Okay, so and then we're done. Save it. Save. Okay, so we're done with the PDE. So the most challenging one is the boundary condition, right? So now let's take a look. So the first one. So again this change from 0 to 1. So the 0 means left, 1 means right. Okay. Now let's work on the first one. So we can hit this one, right? P1 as left, as it means, and s is 0 means x is 0 here. Okay, this is the first one. This is 1, right? P1, and this x0. So you could get u1x so you get u1x t0, right? 0 means SL equal to 0. So I'll write the boundary condition here, right? Okay, now let's compare these two equations. So you get, hey, you get this equal to 0, right? This one equal to 0 because I'm not, and then this one here you will still keep ux, right? So this turn b1 equal to what? b1 equal to u1x, right? And then q1 equal to 1. Okay, so that's how you get q1. So q1 equal to 1, right? p1 equal to, again, this for the left hand side, right? This q1 equal to 1, and p actually was a vector, so you get p1 here, p2 here, right? So p1 equal to, again, 0 means the left, this is the left, and this one is the right. Okay, left means s0, right means x equal to 1. Okay, so therefore p1 equal to 1, 0, right? So p1 equal to 0 and q1 equal to 1, and then b1 equal to u1x. Okay, so you get b1 equal to u1x. You're right. So we're right. Okay, now let's work on the second. So for the second, again, also work on the left hand side, right? For the left hand side here, left, and then we're working on the second one as u2t0. So we get u2t0. So we get this one. Okay, on the left you get u2t0 equal to 0, right? Equal to 0 here. So you get this equal to 0. Okay, so similarly you get so you can see b2 equal to what? b2 equal to b u2x, right? So you can see in this equation we don't have u2x, so therefore we have to push this one to 0. So we get q2 sl t equals to 0, and then after that you compare these two equations, this one with this one, right? You get p2 sl tu equal to u2 t0, right? So you can see here, so you can see p2 u2 here, right? u2 and then q2 equal to 0. So q2 equal to 0. So this is the left hand side. Okay, so we're done with the left hand side. Now let's work on the right hand side. The right hand side, for the first one you get so we need to write this in the standard format. You get u1 t minus t1 minus 1 equal to 0, right? This is the boundary condition. So ut 1 minus 1. So you get this one, right? This is the right hand side. Remember, for the 1, so we get u1 t1 minus 1 equals 0. So therefore, again, we don't have, remember this one is u1x, right? The derivative of u1 over x. So we don't have it. So therefore, we have to push this one q1 sr t equals 0. Right, this one, so this term is equal to 0. So compare this equation here, this boundary equation with this one. Okay, and then you can see we will get p1 sr tu equal to u1 t1 minus 1, right? Because these two equations, so I use the red color. These two equations should be the same, right? Okay, and then this one is equal to 0, so therefore p1 equal to this one. Alright, so therefore we could, on the right hand side, on the right hand side you could get this one, right? This p1 u1 minus 1 and then q1 equal to 0, right? Okay, now in the last one is u2, right? It's also right hand side, but for the variable 2, so we get u2x equal to 0. So we get this one, right? This equation. We get u2x equal to 0. Now remember, this b1 is equal to what? b2 equal to u2x. Okay. So therefore, to keep u2x, we should keep what? We should keep q2 srt equal to 1. So similarly, we don't have anything other than u2s. So therefore, we get you could put p2 srt u equal to 0. So therefore, we get here. Right? So we get, so here this is p1 and p2, right? So p2 equals 0 here, p2 equals 0, and then q2 equal to 1. Okay. Anyway, what you need to do is just compare the equation with the standard format and then try to figure out what is the q and what is the p, right? Okay, now let's type in the boundary condition function here. So we get so we get a new function with function PL Q QL PR QR equal to basically BC function 2. Get SL UL SR URT. Okay, and then we get P1, remember PL, right, equal to 0 UL2. UL means what? So UL here, so you can see, let's take a look. So P1 P, so here, right, so UL means left, right, left, so UL, and 2 means it's 2 here, right? Okay, so that's why UL 2, L means left. Okay, so the R means right, and then this is 1 and 2, right? Okay, remember this one is for the left, this 2, right? This one is to the right. Okay. Okay, so we get UL2, so this is PL. Okay, it's not P1, it's PL. So similarly, QL equal to 1 and 0. And then we're going to have PR equal to UR as the right, index 1 minus 1 and 0, right? And then you get QR equal to 0 1. Okay, and then save it. Okay, and then we get the initial condition, right? Put initial condition here. So okay. Function value initial function 2 x, right? And then we get value. Again, this is a vector, right? We have 2 initial conditions. The first one is s square, the second one is s times s minus 2. Okay, so save it. Okay, the last one is the main function, and then we are done, hopefully, right? Yeah, so again, m equal to 0, right? So save it as main PDE2. Okay, m equal to 0. Again, we need to discretize x and y link space 0 1 with 10 we get 10 sampling points, then with t link space 0 and 1 with 10 sampling points, and then we get solution equal to p d e p e. So similarly, as example 1, we just put the functions name here, but be very careful, right? They should be consistent, otherwise you're going to see error. Okay, S and T. So we get done. We get U1. So we can see SOL, and then we had U1 and U2, and then you can have the first one is the should be the time. This should be the space. Okay. The first one is space. The second one should be the time. Right, and then the third one is for the x and U1 and U2. Okay. So get U1 equal to, so 3-dimension matrix. Okay. This is U1, U2. We get solution here. 2, and then we can subplot means what? We're going to plot two figures together. So this means we have two figures. Each one we have one, right? Something like this. Okay. You could just use help subplot and to figure out how to use it like subplot. So we're gonna have two figures, and each one have one column and then surface. Put, for example, we're gonna get the profile of U1, and then we get title here, U1 S and T. Then we get as label, and then here is distance, distance x, and y label, time t. Okay, and then we get the second figures, right? And just copy. And here we get this be U2, and then this be U2. Other things just be the same. Save it. Okay, now hopefully we get a result. So we get the first one, we get a U2. I don't know why we can get the first one. Let's see. Oh yeah, I forgot. So this I need to put subplot, right? This means we're going to get the second profile, like this, the first row and the first column and the second row, right? This means two figures, and this means the column, and this means the first column. This means the second row. Okay, now let's run it. So we should get the same result as the one we have here. Okay. Anyway, this example are taken from, right, from this document, right? Actually it's from text says AMM. So you could just Google the title of the document, you find it. So we're done with this module.